All right, so welcome everyone. Tonight's event is going to be starting momentarily. We have Dr. Tony Moffatt with us, and you also see with you there in the spotlights, we've got myself, Kareem Jaffer. I'm the Public Events Coordinator for RASC Montreal Center. We have our Honorary President, David Levy, who will speak in just a few moments, joining us from Arizona. Then we're lucky tonight to have two students with us. We have Karosh from John Abbott College and James from Marianopolis College. They're going to be moderating the Q&A because Tony's talk really is fantastic because it covers material that we see at the college level in our science option courses in astronomy at John Abbott and in astrophysics at Marianopolis, and our space clubs cover a lot of this material as well. So it's great to actually have the students involved at the grassroots level for this. Now, before we get started, we normally like to start with the RASC Montreal Center with a land and sky acknowledgement. We acknowledge not only that we're on the lands of shared peoples, but we're also sharing the sky with our Indigenous peoples. And there's always something in the sky that kind of reminds us of the stories from our native roots. And at the moment, we're hitting the full moon in a couple of nights. And the full moon for April is normally known as the pink moon. And this year especially, it's a supermoon because it's actually reaching its close approach to Earth, and it's a very bright, large moon, as you've been seeing the last few evenings. The pink moon is named for the spring appearance of moss pink, which is the wild ground phlox. This is something that has actually been in ancient culture for a long time, and it's even referenced in the first farmers' almanacs of the settlers when they first came over to North America. So when we talk about the stars and the sky and the constellations and even the moon, comets, meteor showers, you name it, we are building on knowledge that we have had shared and brought down from cultures and generations galore. So now, before I go any further with what RASC Montreal Center is all about, I'm actually going to stop sharing and I'm going to turn the floor over to our Honorary President, David Levy, who likes to start off our clubhouses and our events with a readout or an excerpt from a poem, something that speaks to him that evening. So, David, we're all yours.
Thank you so much, Kareem, and welcome. I'd like to add my welcome to his and to all of you. And I think it's going to be a very, very nice meeting. And after it's over, there'll be the almost full moon out in the night sky. Tonight's quotation is going to be from Walt Whitman. And I know we've heard Dr. Moffatt's lecture before here over the years, and we're all looking forward to his remarks tonight, and it's going to be a lot of fun. But the lecture is actually something that I think about when I give a lecture, and I think it applies more to me than it does to anyone else, certainly not to Dr. Moffat. It's called When I Heard the Learned Astronomer, when the proofs, the figures were ranged in columns before me. When I was shown the charts and diagrams to add, divide, and measure them. And when I sitting heard the astronomer, where he lectured with much applause in the lecture room, how soon unaccountable I became tired and sick, till rising and gliding out, I wandered off by myself in the mystical moist night air, and from time to time looked up in perfect silence at the stars. Thank you, and back to you, Kurt.
Thank you so much, David. That was beautiful. It's so nice to start with these wonderful readouts and poems, and it really kind of sets a nice tone for our discussions later on this evening as well. So for those of you it's your first time joining our RASC Montreal Center and the RASC overall, the Royal Astronomical Society is an amateur astronomy society that's all across Canada. We have 29 centers. We have actually close to 5,000 members at the moment. We're the largest, most active group in Canada. And the current Montreal Center here, we've been around for over 100 years, more than 100 revolutions around the sun. And we have over 160 members of all ages. We do a lot throughout the year. And some of the things that I wanted to highlight to you is some of the things we do for our members, as well as some of the things we do for the public in general. So for our members, every Wednesday and Saturday, once COVID began, we jumped straight into Zoom. So we've been having Zoom clubhouses twice a week, which makes us one of the most active clubs in all of Canada. We also, on Wednesdays, have special presentations from members, for members, but also for guests. So you're welcome to join us at any of these Wednesday presentations or at any of our clubhouses to get to know the club. This coming Wednesday, we have a fantastic talk by a local artist and one of the artist in residence directors actually at SETI, Tahina Ramirez, who's our past center president. She's going to be giving a talk about encouraging girls into STEM by fusing art and astrobiology. And then the following Wednesday, we're going to be going over the May night sky, so you can plan out some targets for viewing. Even with curfew, there's still stuff you can see in your backyard. And then the following May 12th, the Wednesday, we actually have a past president of the National RASC and London Center member Peter Jedicke, who's been joining a lot of our clubhouses. And he's going to be talking about globular clusters, which are just fantastic binocular targets, small telescope, or cameras even. So we're going to have those talks. And then one of the big things coming up in the next few weeks is, or in the next month and a half actually, is on June 10th, there's an annular eclipse, which is an eclipse where the moon doesn't quite cover the whole sun. Now, we can't see totality in Montreal, but we can see some part of the eclipse, and actually a lot of the eclipse, right at sunrise. So if you want to know more about the eclipse, you can message us. But there's a link there that will take you to a spot where one of our members, Andrew, who a lot of you know as the night sky guy, he has been setting up a assured solar eclipse glasses website to sell small packs of solar eclipse glasses so you can safely view the sun with your eyes. Now, these glasses are necessary to view the sun, so don't go trying to see the solar eclipse without the proper protection. If you want individual pairs, you can always find them at the local astronomy stores, Maison d'Astronomie or Astronomy Plus in the South Shore. We also do a lot of public events and outreach. We have tonight's event on small satellites, big stars, and then next month we have International Astronomy Day. Now, before I talk about that International Astronomy Day, I do want to mention that for our members, we're setting up a swap table to be done virtually on Saturday, May 8th. If you're not a member and you're still interested, please do reach out to us and let us know, and we'll work with you so that you can be part of this virtual swap table. But the big event that we have coming up after tonight is International Astronomy Day, Saturday, May 15th. And myself and our outreach member, Russell Freilich, we're working hard to put together something that's actually international and global in scale. But one of the big things we're going to be doing on International Astronomy Day is launching a new program that the Montreal Center has been working with the National Education and Public Outreach Group to put together. It's called Creation Station, and it's going to encourage kids interested in space and astronomy to use their imaginations and put together their own stories and illustrated comics about space, astronomy, exploration, everything to do with really the reason why a lot of us got into this hobby, that passion. Now that's all coming up, but we're lucky tonight to have a fantastic talk and a fantastic speaker with us. So without any further ado, I'm going to turn the floor over to Dr. Tony Moffatt. I'm going to ask those of you who have questions, please do post your questions in the Q&A tab, which you'll find at the bottom of your Zoom window. We're going to be collecting the questions throughout the presentation, and even after the presentation, during the Q&A, you can continue to ask questions. And our wonderful student volunteers here, James and Karosh, are going to be taking care of consolidating those questions and trying to cover as much of that as possible. At the end of the event, we're going to migrate over to our Zoom Clubhouse so that everybody can more informally chat, discuss, talk to Tony, talk to each other, just talk astronomy and enjoy our wonderful joint hobby, our joint passion. And at the end of the talk, once the Q&A session is over, I will put the link to the Clubhouse directly in the chat so you can join us. If there's any questions, let me know in the chat. And otherwise, Tony, we are all yours.
I'll start sharing my screen then.
Please, that's fantastic.
Okay, doke. 2 clicks and we're there. One more click, however. Wait a minute, I better make it large first and then start it. So is that okay? Does everybody see that?
That's beautiful.
Good. Well, this is the logo for the featured satellite this evening called Bright, which is I was told by some people, an American spelling of bright, matched as an acronym to what we really mean, Bright Target Explorer. And I won the contest. This was my submission, actually. I'm quite proud of it because everybody calls it Bright. And it started in Canada and spread to 2 countries who collaborated with us, first Austria, then Poland. And for them, it was a really big deal. For Canada, it was a less of a big deal because we already had space efforts in astronomy and outside astronomy too. So anyway, Bright is what we call a constellation. That's a nice name, I think, of 6 nanosatellites. However, they're all in orbit, but one of them, called Bright Montreal, of all names, is not accessible. It never was released properly from its Russian 3rd stage. So we have 5 functioning satellites, nanosats, as we call them. And this is a world first, as you can see here, because it's never been done before, that is to say, using nanosats for astronomy. This is the very first time. Nobody thought it could be done because they don't have much inertia and you can't stabilize them in space very easily. But luckily, it was done in Canada for the first time. So the Bright nanosats are designed for, as you see here in the upper left, time-dependent precision space photometry, reaching over at least 6 months in 2 filters. Each satellite has only 1 filter, though we wanted to avoid any moving parts. That's always a risky undertaking in space when your budget is limited as it is in Canada. And anything brighter than about 6th magnitude, although I myself had ventured down to 8th magnitude almost, and it with success. I'll show you that later. So here's a bit of a cross-section of the inside of the satellite, which measures about 20 centimeters a side. And we have, first of all, on the left, you can see the baffle, which avoids scattered light getting in and spoiling the observations. And the optical cell here contains a system of 5 lenses mounted as such and a CCD detector. It's a very simple thing. You could have been a single lens reflex camera in space, essentially. Would have done the same job. But the choice of the lenses was very important. We didn't want to have in-focus stars. We wanted them to be purposely out of focus. And that gives you better photometry by spreading the light over more pixels. Otherwise, if you're limited to very few pixels, then for bright stars, you have to make many exposures, which you can do much more easily by spreading the light out. So that the images actually look quite ugly. I don't want to even show one tonight. So here's I'd like to get rid of this at the top because I can't read my own screen. Just a minute. If I can move this off to the side. Oh yeah, I can move it away. That's it. Okay, good. More or less. So Bright is actually well adapted to my favorite topic, that of massive stars, and I'll explain what I mean by massive stars in a minute. And there are 2 reasons for that. First of all, most of the massive stars are also bright, and they're found in the Milky Way for the most part, which is a good thing because the satellites can only point basically towards the Milky Way. There are not enough bright stars to lock onto with our small guiding telescope to make this feasible. And of course, long time scales are favored. That was from the start a choice we made. And massive stars, if they vary, often have long time scales too. So that is a perfect match. And here you can see some of the fields in the Milky Way that have been observed and reobserved year after year. And it's still going strong after about, what is it now, 7 years. The favorite field is Orion, and you can see the blue dots, or even purple, are the O stars. The blue are B stars, as you can see from the code on the left here. And all these fields and even more have been covered, and we're just going around, dancing around the Milky Way every year with our satellites. Those that are still functioning, there's a couple of them are having trouble. The detectors have decayed considerably and are not producing good data currently. Okay. I don't know why I can't change the slides here. Wait a minute. Let me get rid of that up there. Oh, that's funny. My arrows don't seem to work. I don't know why. Hang on, let me just see if I can fix this.
Did you want to try exiting out of the slideshow and back in? That might
Maybe.
work.
I'll stop share for a minute. Yeah. Hi. And I'll share again. Yeah, that's a good idea. I don't know why
No
would
worries, that
happen.
happens.
Yeah, sure.
Especially when you're counting on it, it always
Yeah.
happens.
Oh, it's stuck there. Just a minute. Maybe I'll stop
And
full
start
screen
sharing at the
myself.
next
Let me
slide.
see. How do you
Yeah.
do that? Oh, right click. No, left click.
At the bottom left.
Oh, there.
Yeah,
Okay, I can do it actually with the mouse.
Okay,
Mouse.
perfect.
I'll use the mouse from now on. That seems to work. Okay, good. So here's a diagram to show what happens to massive stars. The massive stars are those with masses greater than about 20 solar masses. And they start out as O stars on the main sequence, burning hydrogen. And they evolve into LBVs, luminous blue variables, which are very bright, stable, unstable supergiants, actually. And before they become Wolf-Rayet stars, which is the helium burning phase. And then that lasts about 10% of the hydrogen burning phase, because the helium burning is not as efficient. And finally, after a supernova explosion, it ends with a black hole, sometimes a neutron star, and sometimes for the most massive stars, nothing. It's just complete obliteration of the star. And you see here a plot in German. I don't know how many of you speak German, but it doesn't matter. What it is the final mass before the explosion, if there is one, versus the starting mass. So on a log scale, 1, 3, 10, 30, 100, up to about 10 solar masses, the stars all end up as white dwarfs, and they stay on this line of 45 degrees. That is to say, the end mass is the same as the beginning mass, because there wasn't very much mass loss during the whole evolution, except as a pre-planetary nebula in the AGB phase, which is a wind, a very fast wind, which only lasts a fraction of the lifetime of these long-living stars. Beyond 10, we go back up to the 45-degree line, no change from the end mass compared to the beginning mass, except at about 20, it starts to deviate. And we see here that the winds kick in, especially Wolf-Rayet winds, but also through the whole lifetime of the star, we see that these stars have strong winds. And instead of being an 80 solar mass star up here, it turns out to be several solar masses. So the wind is very, very strong. And I'll illustrate that in just a minute. I took this from a wonderful little book in German by Norbert Langer, a colleague of mine in Germany. Oh, now the arrows work. Okay. So let's have a little quick comparison of stars of different mass. Here you can see M is the mass in solar units, 0.11, the sun, 10 times the sun, and 100 times the sun, or 10 to the power 2. And for each of these variables, which characterize the star, the luminosity, we see that we know that from the theory and from observations that the luminosity goes as the cube of the mass for main sequence stars that burn hydrogen. So a star of 0.1 solar has a very low luminosity, 1/1000th of the luminosity of the sun. Whereas if we step up to 10 times the mass of the sun for the mass, the luminosity is already 1,000 times. But then if we go to really massive stars, close to the upper limit of about 100, it's a million. So one single star then emits 1,000,000 times more photons, more light, than the sun. This is incredible. But it's tempered a little bit by what we call the mass function, the initial mass function, which is here. The number of stars of mass m goes as 1 over m squared, which means that when m is large, the numbers are very small. So when we fold this in and multiply it by the mass, we see that massive stars only make up a small fraction of the total mass. It's really the low mass stars, 0.1, which dominate in this way. And that concurs with what we know, that most of the mass in the universe is locked up in low mass stars. But the luminosity, on the other hand, comes from the massive stars. And we can look at the mass loss rates which vary wildly from even more so than the luminosity, that a single massive star of 100 solar masses has a wind which is 10 to the 10, which is enormous. It's a huge factor, stronger than the solar wind in the rate at which its mass is leaving the star. This makes them very important objects as far as the ecology of the universe is concerned, enriching with products of nucleosynthesis. And I won't go into detail with the rest here. You can look at it and I can explain it later if anybody's interested. Just to cap it all off here, here's the actual mass loss rate of the sun. It's despite the presence of comets and various other phenomena that the zodiacal light, which depend on this, that this is a very small number compared to massive stars, which are more like 10 to the minus 4 solar masses per year, which even that seems like a very little, but it is a lot, believe me. And of course, the age of the sun is about 9 billion years, maybe a little bit more now with more recent estimates. My arrows are working fine now. I don't know what happened there. Anyway, this is a diagram which shows variability of, whoops, it jumped on me, sorry about that, of stars in the HR diagram, which is the diagram of luminosity in log units here versus the temperature, the log, also in logs here. So to the left are very hot stars and up are very bright stars. And so you can see that the main sequence here, which is this dashed line, covers various types of variable stars, their names of which you've probably heard of. Ara Lyrae, for example, which is in the instability strip along with Cepheids. And then as we go up the main sequence, slowly pulsating B stars and Beta Cephei stars. But as we reach the top here, there's nothing, actually. There's no known oscillations systematically studied for the O stars, which is a curious thing, and we wanted to change this. Bright satellites have helped us a great deal to do that. However, an exception to this are the late type O stars, as the star Zeta Ophiuchus, which is a late O star, O9.5. 5 means main sequence, and the precursor of Bright, which was the MOST satellite, and another Canadian satellite, showed this beautiful light curve here. And this is only a small fraction of the total light curve over a month. This is from here to here is 1 day. So this is just 2 or 3, maybe 4 days total out of the total of 30 days a month that this was observed. And in the Fourier transform, which is a way of highlighting different frequencies of vibration of the star, we find many, many peaks. And here they're all listed. Most of them are in several the order of several hours. And this is as expected for a star of this kind, this size. So I won't go into details here. You can look it up in this paper by Gordon Walker et al., who's also retired. He was my mentor in a sense when I was working at the Penticton Observatory. We organized an eclipse expedition. He was at the DAO in Victoria, and we met on a camping trip up to near Yellowknife to watch the eclipse of 1963 as it passed over Canada and the US. So anyway, moving on. But the thing is, the earlier O stars, that is the hotter O stars, don't show many pulsations. And what we think they show now, as I will highlight later, is the stochastic variability, random variability in their light. And we think this is due to various phenomena occurring in both the winds and in the star, the photosphere, the surface of the star. As we progress after the main sequence to the Wolf-Rayet stage, the helium burning stage, these are very bright, compact stars because helium burning is less efficient, so the star collapses a little bit on itself before it can reach a temperature that ignites, in the nuclear sense, ignites helium to burn into carbon. They show that the cooler among them tend to be the most variable. And I'll show an example of that this evening. LBVs are very large, show very large variations, and it's believed due to the clumping effect in the winds. All stellar winds seem to be clumped. That's a discovery that we made here in Montreal back in the 80s, that they all were. And the ultimate source of these surface variability is a phenomenon which was never known before. This paper came out in 2009, a very recent discovery, just, well, 12 years ago now. It's for a bit, I guess, but for me, that's recent. That there's a layer of subsurface convection in the star. It's highlighted here. This is the surface of the star. Most massive stars near the main sequence are very hot, and they're in radiative equilibrium at their surfaces, and the convective zone is usually in the core region. But there's an extra layer here due to an anomaly of iron, which can cause convection to form, and this causes disturbances to reach the stellar surface in a way that we think we observe. So let me go on. I'll come back to that later. MOST, and bright is often called the son of MOST, were developed in astronomy, and both are absolutely 100% Canadian. The idea was started here at the Spaceflight Laboratory in the University of Toronto Institute for Aerospace Studies. And I know the director there, Rob Z, quite well. He helped us out a great deal. And the key to this success was the invention of micro gyros. These are the spinning wheels, of which there are 3 in 3 directions. They had to be very small to fit in the small telescopes. And the ones in Hubble, for example, would be the size of the telescope itself, in our case, or larger even. And this enabled us to stabilize pointing to about 3 seconds of arc with MOST and 10 seconds with bright. Bright is lighter, so it has less inertia, and it's much more difficult to keep pointing to an object in the sky and do good astronomy. But 10 seconds is okay because we have pixels that are about 30 seconds. That was chosen so we can have a wide field. So it all fits together and works out beautifully. I was a member of both teams, MOST starting in the mid-90s, and then bright starting in the 2000s, the early 2000s. So here, I'd like to highlight a few bright results for massive stars with 3 examples. One is an O star called Zetapuppis. You probably may not have heard of this star. It's only visible in the south. It's in a declination of -40 degrees. Visible in January, the best, but it's still visible now, I guess. And it shows co-rotating interaction regions, CIRs, as I call them. I'll explain what this means in a bit more detail later. And clumping in the wind. And then I'll highlight 2 single Wolf-Rayet stars with their names here from a catalog. It's kind of a boring name, this one shows clumps only so far, and this one only shows CIRs, which tend to be semi-periodic. And I'll discuss those and what it all means. Note, I just added in the bottom here that Wolf-Rayet stars are actually hidden from view. Their surfaces are hidden because their winds are so strong. And this is quite in contrast to O stars, where we see the photosphere. We see the absorption lines coming from the photosphere. So first, Zetapuppis. There, okay. There it is. Whoops, it goes too far. Okay, there we go. There it is on the sky. There's nothing special about it. It's just a bright star, 2nd magnitude, easy to observe. And with our small telescopes, the exposure times are typically about 1 second. And with that, during a whole orbit, we combine all the measurements in an orbit. We get a precision of about 1 millimagnitude, 1,000th of a magnitude per orbit of bright. And each of the orbits are about 100 minutes, low Earth or relatively low Earth orbit. And this was a project of my last student, PhD student, Tahina Ramirez. I've got his name down pat now. I've practiced this quite a bit. He is now a postdoc at Arizona State University in Phoenix, Arizona. And Tahina is originally from, where is it now? Just off the coast of Africa, not Mozambique, what's the island? Madagascar, yes, sorry. And he came to France first. He speaks French fluently. That's why it was easy for him to come to Université de Montréal. And his English is excellent too. And he wrote the paper with some guidance from me, but he did most of it himself, his study of Zetapuppis. And in his work, we have the first discovery of a direct link between what happens in the surface of a massive star, hot star, and it's the wind that surrounds it, that it drives. This was not known before. And Zetapuppis is a runaway star after a supernova explosion, we believe, of the primary. It was a binary, and the two stars separated because there wasn't enough mass to hold them together after the supernova. And it has a measured velocity, a peculiar velocity, we call it, in space of about 60 kilometers per second, which is high. Most stars have a noisy distribution of about 10 kilometers per second, most young stars in the Milky Way. It's hot and luminous. Its temperature at the surface, effective temperature we call it, is 40,000 degrees. It's second magnitude, and it's a fast rotator. Although it's even faster once we get this I factor. Sin I is the projection angle of the axis of rotation on the sky. And as we'll see later, I is quite small, so it makes V, when you divide 220 by a small number, you get something large, and it comes out to about 500 kilometers a second, which is huge for a massive star. Most massive stars have rotation speeds at their equators of about 100, 150 kilometers per second. Now, the bright observations lasted about 6 months, and we saw bright spots, and some of the photometry we saw from the Fourier analysis, I'll show in a minute, it gives a period of just over 1 day, between 1 and 2 days, and the inclination angle which we deduced from the variability is about 25 degrees. This is the most massive star observed by Bright so far, with an estimated mass of 56, although a recent study showed that this is probably a bit too high. Many things are happening in astronomy, new discoveries of new kinds of objects, but also refining our knowledge of what we thought we knew before. And it hangs together much better when that happens. So here are it's a complete light curve from 2014/15 of Zetapuppis with 2 filters, with 2 different satellites, blue filter and below it a red filter. And then each panel shows a continuation of what was before in the previous panel. So you see from here to the top panel, it's about 40 days, a month or so. And this continues over for about a little over 5 months. And you can see, if you have good eyes, you can see that what happens in the blue seems to also happen in the red. That's very interesting. Why don't usually most stars show a strong color dependence? If you look at Cepheids, you should see an increase in amplitude as you go to the blue. This is not the case here. Instead, we see when you plot the blue magnitudes versus the red, you see almost a straight line. This is the orbital means of Bright plotted, and here are the residuals, which I'll explain in a minute. And the slope is very close to 1, which means what happens in the blue filter also happens in the red filter, essentially. And we want to, of course, explore this part, but perpendicular to this line is the scatter, is the instrumental scatter. And that turns out to be, if you do a plot across like this, you get a Gaussian curve like this, which leads to a sigma, a standard deviation, which characterizes the width of this curve of about 2 pixels. Sorry, 2 millimagnitudes. Yeah, that's right. Plus or minus this number here. So because we're comparing 2, that means 1, you divide by root 2, you get just a little bit less than 2 millimagnitudes per observation, which is pretty good. That means we're doing precision photometry. You can't do this from the ground. It's almost impossible, even from Arizona, even from the mountaintop, or Chile. So this is at the left, you can see the Fourier analysis, and we see 2 periods. One here, the prime period, and the second harmonic, which is exactly twice that, and then possibly higher harmonics, but at some point they disappear. And this is in the blue filter and the red filter, exactly the same thing. It's been inverted just for convenience, so we can show it in one plot. And in the sub panel here, you can see over a longer scale in time. And in the middle panel, you can see once we decide that this is the basic period of 1.7 days, this is frequency of just below 0.6, and when you invert that, you get the period in days. This is frequency in cycles per day. So just take 1 over 0.6 and you get 1.78. 1.78. And when you phase up the data with this period, putting all the data points in the same interval, then you find this very broad curve, but the mean values follow a nice average, as you can see here, for both satellites, and they're both about the same. And if you plot just these means versus each other, you get a very tight relationship here with a slope of very close to 1. And again, you can determine the scatter perpendicular to this, which is the instrumental scatter, and it's about half of a millimagnitude because we've taken out means from each orbit. But very interesting is actually just as interesting as the period is the scatter about the curve. This is the first time this has been seen in a star, and the reason for that we believe that is that it repeats itself from the blue to the red, so we know it's real. That was very important, it turns out. So here on the left, you see the Fourier analysis as a function of time. It's useful to see how stable is this. And you can see that it's not terribly stable, it does change. And when you phase up the data, you see the two peaks here. Sometimes there are two peaks, which would favor this harmonic. Sorry, this harmonic, yeah. We tend to see two. And when we see one, we tend to only see one, the prime frequency, we only see one variability, one hump on the light curve. And we can divide this up into several sectors in which the variation is more or less is constant. Okay, and so Tahina managed to do an inversion of the light curve to the surface of the star. And this is a complicated process, but it can be done. And he finds that for these 3 parts of the cycle that he observed, the shape of the average light curve changes a little bit. And some of the points, bright spots on the surface of the star are necessary. This is a longitude-latitude picture, changed a little bit with time. And here are the 5 sectors that we showed in the previous one. You can see that some of the spots are new, and some are, this one is the same as this one, I guess, and it's just fading away, and it's gone here later. So these spots last for several weeks, if not months, the ones that cause the periodic variability. But we also luckily had spectroscopy, and this was obtained for us by amateur astronomers in the Southern Hemisphere, especially in Australia. There's some in Brazil, and none in South Africa, unfortunately. Would have been nice to fill in the time, but this was sufficient to do a very thorough study of how the lines in the spectrum vary. And the most famous line, the most useful one for us, is one that comes from the wind. And that's due to the line of helium. We often see this line in emission instead of absorption. It comes from the wind. And when we do a Fourier analysis across as a function of position on this line, we find a power peak at the same frequency as we saw with bright, completely independent. So what's happening in the photosphere, the star, which bright measures, excuse me, we also see in the wind adjacent to the surface of the star. So that's very exciting, actually. That shows the connection between the surface, what happens in the surface, and in the wind. And you may think this is getting a bit pedantic, and why bother? What's all the fuss about? But this is really frontier astronomy, and to understand these massive stars completely, we need to do this basically. And let's not forget that massive stars are the ones that provide the most heavy elements to feed the rest of the universe, to make planets, and to live on as we are now together. And as far as the periodic variability is concerned, we have a model which I'll show us a schematic of this in a minute, called CIR modeling, co-rotating interaction regions. It's seen in the sun, and it was thought that something like this is probably apparent in these stars. And you can see that if you break up the data into three logical sectors, as has been done here, you can see that the pattern that this model makes changes a little bit with time. And these are the observations, and the model matches them surprisingly well. And I'll show you in a minute what I mean by these CIRs. More detail. Oops. Try this. There. Okay. Okay. And another thing that was a surprise to us was that when you look at other lines in the spectrum, besides this helium line at 4686 angstroms, in H alpha and H beta hydrogen lines, and compared to bright, you see there's a shift. You can see that these peaks are shifted a little bit. And it's summarized in the plot in the panel at the top here. And this implies that what happened at the star is seen a little bit later. As the star rotates, this shock that is perturbing the star, the CIR, has moved on a bit. And you'll see why that is in just a minute. At the same time, luckily, at least later, I should say the bright data I'm showing here were from 2014-15, but later we got some Chandra time, the X-rays, which is the big telescope like Hubble, but to measure X-rays, NASA telescope, and we obtain a whopping 820 kiloseconds, simultaneously with the broadband data light curve of bright. And this stretched from 2018 through 2019. There are many gaps, but the Fourier analysis of the Chandra data, lo and behold, here is this 1.78 day period. There are lots of other periods because there are gaps in the data, and they tend to do this. And there's another 5-day period which was seen before. I observed it in Chile, the star Zetapuppis, and found this period. So we're tracking this down. We're not sure what that is, but it's very exciting to see that we see the same period in X-rays, which must come from the wind, shocks in the wind, as we see in the surface of the star. And here are the light curves of both bright and at the bottom here, and Chandra in counts, X-ray, counting individual X-ray photons as they arrive. This has been normalized though. So the amplitude is much higher. The relative amplitude is about 7% from peak to peak in the X-rays, and with bright it was only about 10 or 20 millimagnitudes, which is very small. But nevertheless, it's there, and you see that the time of maximum bright light does not coincide with maximum X-ray light, and there's several reasons for this. And it depends if you match this up with this peak, the two peaks, then it gives a time delay. However, if you say that the X-rays are reflecting something different, and we match up the two peaks, just the phases, the times, then this requires that the phenomenon, that spots that are producing the optical variation don't produce always the same or relatively same X-ray variation. They're quite different. So here's a picture of a simulation made by Pranmar and Iwaki about 25 years ago, which is one of the most quoted papers in astronomy. And they show two of these co-rotating interaction regions. They're shocks caused by bright spots on the surface of the star, here arbitrarily with two of them, one on opposite side of the star. And they cause perturbation that propagates out through the wind, but the star is rotating. So you get a spiral, an Archimedes spiral essentially. And we see that if the bright continuum comes from here at the surface of the star, H beta emission here, H alpha further out, and 4686, and X-rays, that is a nice sort of progression, showing that possibly we're seeing for the first time some kind of this structure, this co-rotating interactive structure. Okay, so after we deal with this periodic variability, we can look at the stochastic variability. It's also interesting. It's quite significant because at the bottom here you can see a comparison star. It's also slightly variable, but not nearly as much. Iota Carina, I think it's called, an A-type supergiant, which doesn't show much variability. And here the red and the blue light from bright of Zetapuppis, which still show considerable variability after subtracting off the 1.78 day period. So what is this variability? We think it's, and before I conclude on that, let me say that the spectroscopy showed similar effects, that there was a correlation between the spectrum. If we had a lot of spectra, you can follow through the night, several nights in a row, and see that these features in the wind tend to propagate out. If they start on the red side, they become redder, the Doppler shifted, and those on the blue side become even bluer as these clumps propagate and accelerate out in the stellar wind around the star. And this graph here shows that there's a direct correlation between what happens with bright compared to these variations, but I won't go into details. I think I'm running out of time. Anyway, we believe that this is a direct link between bright spots in the photosphere and CIRs on one hand, which are semi-periodic, and clumps, which are short-lived on the surface of the star. And these are due, we think, to a convective zone, a subsurface zone, which perturbs the matter in the star such that it creates waves and perturbations which reach the surface. And the calculations show that it's depressed a little bit, so we see they should be hotter. The star gets hotter as you go down into the star. This is the surface of the star. The center will be down below in these two papers. And so the long-lasting CIRs are probably magnetically controlled. This remains to be proven, but that's the suspicion. Whereas the clumps do not have a magnetic field. They're less stable. They come and go. You need a magnetic field to stabilize plasma or gas. So this is getting a bit hairy and complicated, but I just wanted to end this part on Zetapuppis showing you a comparison of bright with a much more expensive and still orbiting satellite, which was launched just a little over a year ago, called TESS, which its main goal was to image and do photometry of stars looking for planets. And it's doing a really great job. But it also observes other stars that happen to be in the field. And one of them was Zetapuppis. At least you can see the colored curve here. And the bright data, which are in black dots here at the same time, seem to follow quite well, although with some additional noise compared to the TESS. TESS is a larger telescope. It's 6 inches compared to our 1 inch. So it has a higher precision and higher sampling rate. But nevertheless, bright could observe for 5 months. TESS can only sit on this for about a month. So we have a great advantage. You need this long time series, even if it's slightly less precise, to nail down the frequencies. They become much better, as shown in the next slide. This is actually simultaneous data. Bright on the right and TESS on the left. And you can see that the Fourier spectrum as a function of time shows the same thing. This is the same as here. It looks a little different, but it actually is quite similar. And the overall Fourier spectrum is quite complicated. When you don't have enough data, you see all sorts of what you think are periods, but they're not. They disappear when you take a much longer sample. And the reason for that is that some of these blobs are random, these flare-ups of light, and so they're canceled out when you have at the same frequency. There's no other variation, or very little variation in phase with this, and so they drop out. So that you can, what we're left with bright is the fundamental frequency, the second harmonic, and even the third harmonic seems to be showing up here. Whereas in the test data, first of all, the peaks are much broader, but there are many more of them, and this is caused by random events on the surface, bright spots, I guess we call them, for lack of a better expression. And this shows that TESS is good, sure, but I think bright outdid it in this case. And bright only cost, each bright satellite cost $2.5 million, whereas TESS probably cost of the order of 200 or more million. NASA. We are poor in Canada, I'm afraid. Okay. So I'm not sure how much time I have. It's 10 to 9. Can I have another 15 minutes or so, Karim?
Yeah, 10 to 15 is fine.
Okay, great. Let me go quickly through the Wolf-Rayet stars. This is an interesting star. Here it is. Whoops. It's a WN8 star, a cool Wolf-Rayet star, quite variable, with a mass estimated to be around 35 solar masses. And this is the faintest star that has been purposely observed by Bright so far. I stuck my neck out here and it worked. And it's surrounded by a nebula, which we see in the next picture. This is I don't know if it's a Hubble photograph. I just downloaded it from the internet. And the central star is here, and it's slightly elliptical. And this star is that's WR40. And for comparison, I show another star here, which shows also a nebula around it, but at an earlier stage. It hasn't formed a cavity in the center yet. It's just starting out. It's another WNH, cool WN star. N is nitrogen, and that comes from the hydrogen burning CNO cycle, where nitrogen is enhanced at the expense of CNO. These elements act as catalysts in the nuclear sense. It's chemistry, I guess, but it's in a nuclear sense. They're called catalysts. So anyway, this nebula is caused by the fast Wolf-Rayet wind catching up and pushing back the slow wind of the LBV stage, which preceded it. Before that, there was the O-star phase, which must have blown a giant cavity around the star. But now we see the Wolf-Rayet wind, which is very dense and hot, pushing back the LBV wind. It might have been a red supergiant, but I think in this case it's probably an LBV. So here's the bright light curve of this star. It's chaotic. There's no frequency, with many frequencies actually. And these are, I would call them false frequencies. They're due to just events that happen. You know, when you have one hump here, you're going to get a Fourier peak, but it's diluted by all the rest of the data. And what you end up with in the Fourier spectrum is a whole bunch of peaks at the low end, low frequency end, with no outstanding single peak. So we have this forest of peaks. And if we had an infinite time series, which we don't have, of course, but if we did, all this would merge into a sort of continuum varying like this. And if TESS observed it, you'd only see a few of these peaks. Very interesting, I think. So this is the time frequency spectrum. This up above is the whole Fourier spectrum of all the data. And you can see again, it's kind of random, stochastic. And here are some details, but I'm not going to go into it now because I think I'm running out of time. I'd rather go on and show pretty pictures rather than reading the text here. So let me go to the next slide. Oops. Yeah, here is a simulation with a colleague at West Tennessee University who works on this sort of thing. It's a simulation of the light curve using stochastic clumps defining the wind, and with a power law distribution, that is to say, very few big clumps and more smaller ones, versus one of constant clumps. And unfortunately, we didn't see any difference between the two compared to the original data, which is quite a surprise to me, and I have yet to understand why that's not the case. And comparing the case A and case B with a spectrum of clumps of different sizes with no spectrum, it's constant size, compared to the data in black here, the distribution of their size as measured from the photometry, delta M, the change in magnitude, the bumps on the light curve, is similar. So this is inconclusive, but it shows that at least it works. It's a random process that explains the observations. And here you see the time frequency plot for the simulations, both of them compared to the original data. So here's the other Wolf-Rayet star. It's called EZ. The Americans call it EZ, of course, but it's not an EZ star. Canis Majoris, it's WR6 in the Wolf-Rayet catalog. And this is also surrounded by a nebula. About 1/3 of Wolf-Rayet stars are surrounded by their nebulae. It's believed the others had them too, but they are a little older and they've blown them off. We can't see them anymore, they're too faint. So here the central star is not this one, but it's this one here, the blue star. It's very hot. And it's not quite in the center, as you can see, because this is a runaway star too. It's moving that way. Anyway, this is a very beautiful picture. As you can see, it's later in the stage of nebulae, unlike the one I showed before, both of them actually. Okay, so this is the light curve of EZ Canis Majoris, which shows variability on a beautiful variability. It looks semi-periodic, and if you do an analysis, you find a period of Fourier analysis of 3.76 days. So this means that our interpretation is that the star is rotating around it with that period, and we don't see the surface of the star, we see only the wind. So we think there are CIRs created by spots which we don't see on the surface of the star, poking their noses out of the wind. And the Fourier analysis shows this. The 3.76 day period is here, and the second harmonic is even often stronger than the first harmonic, as you can see here in the analysis of these. But we also see the third, this is the second, the third, fourth, fifth, and even a hint of the sixth harmonic of this. And the reason for that is the shape of the variability is not sinusoidal. If it were sinusoidal, we'd just see one peak. And this is a time frequency plot of the same thing, essentially, showing that the domination of the second harmonic occurs sometimes, and then other times it's the first harmonic, the fundamental frequency. And that's because it resembles a sine wave a bit more here than it did here. There are probably two humps in the light curve. So the light curve is variable. And to reflect that, we've done this. I love this plot. It's a plot of the light curve, color-coded according to the numbers here. Bright is up and faint is down, blue. And it shows what it must be happening at the surface of the star. Although we don't see one pixel on the surface, we see the whole hemisphere of the star as the rotation cycles continue. And you can see that this spot here that was we believe was on the star that caused the bright light curve must be rotating with this same period, because if you take the wrong period, look at this, if you take, instead of 3.76 or 756 days, you take 3.70 or 3.80, everything is shifted diagonally. That's the wrong period. The right period is this one here. And it shows that whatever is happening at the surface of the star, it is repeating itself, but only for a few cycles, maybe 10, 15 cycles. And then it changes. This spot on the star ceased to exist here, and it's replaced by other spots. So I think we're onto something here, and we have to follow this up. There are spectra obtained by amateurs, again, in South America, in the Southern Hemisphere, Australia in particular, which will be used to analyze this in more detail. And just to show, this is the periodogram, the Fourier spectrum of the, again, showing the nature. The peaks are not sharp and simple. They're broadened. They're by what we call Lorentz functions. And this is exactly what you expect for a phenomenon that is semi-periodic. It's periodic. The star is an exact clock with a period of 3.56 days, but the phenomenon on the surface of the star does not last more than 5 or 10 rotations. So they come and they go. And this is exactly what you see here, this Lorentz curve. The same phenomenon occurs studying atoms in a hot gas. You get Lorentz broadening of the spectral lines. So this is not new to physics. And again, we looked at this. This was done before, actually, previous work from the ground. A student of a colleague of mine from France studied this. These are the data, and this is a simulation. You can see there's a similarity, but it doesn't fit exactly, and it needs a little more work. The pattern that needs to be proposed to match the data over on the right here would be a little more complicated than just two oppositely posed bright spots on the star. Maybe one here and another one here, and not necessarily have the same strength. So we have a bit of work to do to sort all this out. So in conclusion, for EZ Canis Majoris, it's quite clear that I think that we're seeing CIRs poking out of the wind in rotation. This is a rotation period. And these CIRs, co-rotating interactive regions, come and go on timescales of about a month. And they're driven by bright spots. That's the model that shows that that's possible. And we don't see these spots at the stellar surface. We propose that they must be there. But the existence of something that's linked to the star in the wind, the strong wind, means maybe we have a way to probe the inner thick wind. This remains to be studied in more detail. So overall conclusions, these three highlighted stars show the following. For the O star, which is we're learning now is quite typical. We have other stars observed, like Zetapuppis, which was sort of a Rosetta Stone object in a sense. We see both phenomena, stochastic, short-lived bright spots. This is universal. All hot stars show clumps, random clumps in their winds. And also the CIRs, all O stars show CIRs as well. And these are driven by bright spots that are more permanent on the surface. The bright spots that produce clumps come and go in time. And as far as the two Wolf-Rayet stars, in one of them we saw a random variability. We didn't see any evidence of a period CIR, so either it doesn't have CIRs or we can't detect them. The other star, it's the reverse. We don't seem to see obvious clumps, although I think they must be there. We just haven't really studied them, highlighted them yet. And both of these phenomena may be also universal to Wolf-Rayet stars. That remains to be seen. So with that, I think I'm done, and I call this the orbiting TMT. So those of you who are aware of the 30-meter telescope that's being constructed probably on Mauna Kea, although there's some discussion going on now whether it's illegal. Indigenous people aren't too much in favor of it on their sacred mountaintop, so that remains to be resolved. And instead of, though, for me, for bright, M stands for millimeter instead of meter. So there. Thanks very much for listening. I hope you enjoyed it.
So we have a couple questions.
Okay.
First question is, why is it better to take the images out of focus? Is it only for calibration?
No, it's to get higher precision. When you spread the light of a bright star out over many pixels, you can you can measure a very bright star that way, which you cannot do easily if you concentrate all the light on a in focus, very sharp image, because then you will saturate the detector. And so we knew we would be measuring bright stars, but we wanted a very high precision. So it was a way to get that. With the MOST satellite, there's a lens which spreads it out in a more uniform way, called a what is it called? Oh, I forget now. Sorry, and it spreads the light out instead of on a few pixels onto about 1,500 pixels, and you can really enhance the precision of the satellite, in this case MOST. And that's the data I showed with Zeta Ophiuchus were obtained that way. The error bars on each data point are very, very small. So I hope that answers the question. If not, fire back at me.
No, I think it answered pretty well.
Okay, good.
Next question is Orion the favorite field because of all the star formation in the nebulae?
Well, it contains a lot of massive stars. The brightest star is Betelgeuse, is a red supergiant, of course, but Rigel is a blue hot supergiant, and there are other stars that are late O stars. It has a lot of very bright O stars, about a half a dozen, as well as a few other stars in the field which are of interest. And it's just the field, the most obvious field to observe. And in fact, you can see in the bright logo here, we've shown Orion, and that's about the field size we have, 24 degrees. So Orion fits on beautifully on the detector. So we can observe all these bright stars in Orion simultaneously, which is nice.
Alrighty, and the last question is, if the bright star has closely orbiting exoplanet, would it be confused as a variable star, or would there be a clear difference in the shape of the luminosity curve?
The light curve, I guess that means. Well, this was never designed to look at late type stars having planets. That will leave to other satellites. We don't have the precision or the cadence and the ability to point to a large number of stars. Although I must say, nevertheless, one of our colleagues will be looking for random or periodic variations due to eclipse transits of planets across their stars. Maybe we'll be lucky and find one or two very bright stars that behave that way. But they're hard to find, even with Kepler, whose mission and test now, of the hundreds of thousands of stars they look at, only a small fraction actually show eclipses. I know there are somewhat around 4,000 stars which do show these transits now known, but that's a very small number compared to the total number of stars that were looked at. So the chances of finding this among the 700 or so stars that have been observed by Bright, maybe one or two stars might, if we're lucky, might show this effect, but nobody has found anything yet. So that's the way it is. Sorry to be negative on that, but that's the truth.
No, no worries. That was all the questions asked.
Okay. Are there any others?
Yeah, I'll carry on with the 5 other questions that I have right now. Okay, so first of all, it's from Dr. Malone. It never ceases to amaze me that a 1-inch telescope produces light curves with milli-magnitude precision. Could I ask why the instrumental sigma seems to differ a bit with the target star? Does this have to do with background flux or camera geometry or anything else?
Well, this is the basically the Poisson noise. With the photons we get, it's maybe 3 times the Poisson noise, which is pretty good for photometry. And let me just show one of the light curves, the Zetapuppis one here. I have the light curve at the beginning. Let's go back to it. Good. Sorry, not here. Back to before that. There. Oh, there's no error bars here, but you can see that the scatter, if you can imagine a smooth sort of curve going through these variations. The scatter is about a millimagnitude, between 1 and 2 millimagnitudes, as you can see from this curve here. So that's only a small factor greater than the Poisson noise, which is the noise in the photons themselves. So with these small telescopes, and even the bright stars, we couldn't do any better. Partly that, well, that's to blame, but also the fact is that we couldn't expose any more than about a second, and the readout time was about 20 seconds, which is fast, but not fast enough to do a lot. And we had to leave the field after about 20 minutes typically, because the orbit, the field would come into view in the next orbit, and the Earth shine and so on, sun and moon and so on would interfere otherwise. So we had about 20 minutes of each 100-minute orbit to sit on the star. And during those 20 minutes, we only had 1 second of observations typically every 20 seconds. So readout 20. So we're slowed down by these processes. And to get around that, we would have had to spend far more money to do it. This is on the cheap. Let me tell you, $2.5 million for one nanosat that works like this, producing wonderful data, publishable results is quite cheap.
Perfect. Thank you. For the next question, someone asked, is there a central citizen science project or a variable star database which would tell amateur astronomers which spectra are being sought to help research like yours?
Well, of course, there's the famous AAVSO in the US, in Boston, Harvard, actually. You've probably heard about this, the American Association for Variable Star Observers. And they welcome input from especially photometry, but I think they're getting into spectroscopy now. And so please contact them. My former postdoc, who worked on bright data, is now in charge, or works for the AAVSO. Bert Pablo is his name. You can tell him, if you write to him, you can tell him you know me and he knows me, so maybe that's an in. And there's a group in Germany that does spectroscopy. And my former student from Germany that did his PhD in Montreal about 20 years ago, Thomas Eversberg coordinates this group here. And I've given talks to them as well by WebEx, like Zoom, and in person a couple of years ago. So they're spectroscopists, amateur spectroscopists in Europe. And there's some in France as well, but this German group is really a leader as far as I'm concerned. I can give you the coordinates, how to reach them if you want. I don't have them readily available now, but if you send me an email, ask Karim to send on your information that you want, and I'll answer this gladly. Does that help?
Yep, I think that should help.
I should add, though, that these amateurs that do spectroscopy are really getting into the physics of the problem, and they really enjoy it. It's a little more challenging than just doing light curves. I think we need both, but light curves measure the continuum in the star mostly, whereas spectra allow us to zero in on lines. And lines come from not necessarily the same part of the star as the continuum.
For the next question, Serge asks, where can I read more on this topic?
Well, there are a few books, but not too many. There are symposia proceedings which are produced. You can actually probably Google something like that, Hot Star Workshop Meeting. I've organized 4 of these myself with colleagues in Quebec province over the years, but they're probably too technical for a more layman's view. Then there are other more popular books that you can get a hold of, and I can only suggest you Google it now and find out for yourself. I can help you if you want, but not right now.
Perfect, thank you. For the next question, Randall asks, how do you orient detect the nanostats and hold them on their target stars?
Yeah, well, that's the biggest challenge, of course. There are, first of all, magnetic torquers, which use the magnetic field of the Earth to rotate the satellite in a rough way. And once the field is attained, then the gyros come into action. And by accelerating a gyro in one axis, there are three axes perpendicular to each other. By accelerating or decelerating, you can swing the telescope a little bit and make corrections and keep it on the field to within about 10 seconds of arc jiggle. That's about the best you can do, which is pretty good. It's fine because we chose pixels that were quite a bit larger than that, 30 arc seconds. And so we can't observe close binaries very well that are closer than a few arc minutes from each other. It's mainly for bright stars, and they are far and few between in the sky as your eye picks them up. Those are the stars we observe, the naked eye stars, basically, with the satellite from space. And it's very important to be in space, of course, outside, above the Earth's atmosphere. And there's there's a night and day if you're in low orbit, but you have no clouds to interfere. You get each orbit, satellite orbit, you get data without fail, as long as the satellite's detectors are working.
Perfect. Thank you. And the last question from Stephen is, what is the microsatellite orbit altitude? Are there hundreds of new low Earth orbiting internet communication satellites problematic for research? And thank you. Excellent presentations.
Well, the Brights are nanosatellites. MOST was a microsatellite, to get that straight, but it doesn't matter. Both were at about 800 kilometers above the Earth's surface. The Hubble Space Telescope is about 500, so a little bit above that. This is still called basically low Earth orbit. It's not in synchronous orbit like some satellites at all, for example. I would entertain any extra questions on the fly if anybody has one. If not, that's fine too.
Thank you so much, Tony. I think there may be some questions that will come up during the chat in the Clubhouse if you'll join us there.
Great, yeah, sure.
For those of you that would like to join us in the Clubhouse, I put the link into the chat of the Zoom, and I will stay online for the next 5 minutes or so that people can access the chat, copy paste, or join us in the Clubhouse Zoom. But on behalf of the RASC Montreal Center, our public events and outreach team, our board of directors, I wanted to thank, first off, our student moderators. They did a fantastic job. Thank you, Gyros from John Abbott. Thank you, James from Marianopolis. It really is wonderful to have the youth involved in something like this. And then I want to thank you, Tony. For those of you that aren't aware, the RASC Montreal Center has had a long-standing relationship with Tony. He helps us out to have our presence during Earth Hour in March at the Victoria Hall at Westmount. We have a star party in September's during non-COVID times at Summit Circle in Westmount, and he helps us sometimes organize that. And one of the big things is getting the city to agree to turn down the lights so we can show just a little bit more than what you can see on a normal night in Westmount. And so we love having Tony come and join us to give a really nice scientific talk every couple of years. Last time actually was a fantastic talk that he gave us about 3 years ago at the Arbo in the fall. And that was a lot of fun because afterwards, I think we stayed on the field till almost 1 in the morning.
Oh, no, I not that late. No. I'm not.
Well, you left a bit earlier, but a lot of us stayed on.
Oh, yes, I wasn't there. No, I'm not a night owl anymore.
No.
I don't stay up nights, I'm afraid.
No worries, no worries. That's why we have our Zooms early, is those people like
a good idea.
David gets to just jump outside at the end of our Clubhouse and still have a whole night of observing ahead of him. So yeah, we were very happy to have David here at the start as well to give his welcome. And last year, right as COVID started, Tony had actually been lined up to give a talk at Marianopolis with the Mary Space Club. The student club was going to host him for an amazing talk on just some of the exciting things happening in astronomy. And it was the second thing that we had to cancel when COVID hit. So I'm really glad that we got a chance to have the talk, or have one of your talks, this was really interesting. So I'm hoping we'll keep a conversation going in the Clubhouse. Please do join us. And again, keep an eye out in your email for our May 15th International Astronomy Day event. Thank you, everyone. Have a wonderful evening. And again, I'll stay here for the next few minutes so that the Clubhouse link is there.